with the p-type impurity. And here the term bipolar indicates that both electrons and holes contributes in the flow of current. Now if you look inside this BJT, then there are two p-n junctions. One is between the emitter and the base, and second is between the base and the collector. And it appears as if the two back-to-back diodes are connected in the series, but actually it won't behave like that, because when we connect two back-to-back diodes, then we are assuming that there is no interaction between the two diodes. That means these two diodes are operating independently. But in case of the BJT, actually there is an interaction between the two regions. So if we connect the two back-to-back diodes like this, then it won't behave like a BJT. Now if we talk about the internal construction of the BJT, then the emitter is heavily doped, and the function of the emitter is to supply the electron. And in fact, that is why it is known as the emitter. Then if you talk about the base, then it is lightly doped, and the doping concentration of the collector is between the emitter and the base. That means the collector is the moderately doped. And if we talk about the width of these three regions, then the base region is much narrower compared to the two regions. So in terms of the width, the collector region is wider than the other two regions, because the job of the collector region is to collect the electrons which is supplied by the emitter. And in fact, that is why it is known as the collector. Now depending on the relation, the emitter base VB and the voltage at the collector is VC, like to forward bias this base emitter junction, the voltage of base should be greater than emitter. And similarly, to reverse bias this collector base junction, the voltage at the collector should be greater than base. That means to operate the BJT in the active region, we can say that the collector voltage should be greater than base voltage, and the base voltage should be greater than emitter voltage. So once this condition is satisfied, then the BJT will operate in the active region. Similarly, in the cutoff region, both emitter voltage then the region of operation, the emitter base junction is forward biased and the base collector junction is reverse biased. So let's say the voltage at the emitter is VE, the voltage at the base is VB, and the voltage at the collector is VC. Like to forward bias this base emitter junction, the voltage of base should be greater than emitter. And similarly, to reverse bias this collector base junction, the voltage at the collector should be greater than base. That means to operate the BJT in the active region, we can say that the collector voltage should be greater than base voltage, and the base voltage should be greater than emitter voltage. So once this condition is satisfied, then the BJT will operate in the active region. Similarly, in the cutoff base voltage, and at the same time, the collector voltage should also be greater than base voltage. That means in this region of operation, the base voltage VB is greater than emitter voltage. Apart from that, base collector junction is forward biased. This region of operation is forward biased, and the collector base junction is reverse biased. Similarly, if we talk about the PNP transistor, then in case of the active region of operation, this base emitter junction is forward biased is greater. So when region transistor operation, so here to the NPN transistor, but here the direction of the arrow will get reversed. So now the current will flow from the emitter towards the base region. Now as I said, when the BJT is used for the amplification of the signal, then it is operated in the active region, and there are different ways to configure it. So in case of the common emitter configuration, the emitter terminal is common between the input and the output. That means in this configuration, the input signal is applied between the base and the emitter, and the output is measured between the collector and the emitter terminal. Similarly, in case of the common collector configuration, the collector terminal is common between the input and the output side. And likewise, in the common base configuration, the base terminal is common between the input and the output side. So each configuration has its own advantage and disadvantage, and we will see all these configurations in detail in the upcoming videos. But in short, depending on the requirement and the application, the BJT can be configured in any of these three configurations. Alright, so now let's understand the working of the BJT whenever it is operated in the active region. And here, we will take the example of the NPN transistor. Now before we understand the working, let me just clear the notations which is used for the supply voltages. So as you can see over here, for the base and the collector supplies, double subscription is used. That means here, this VBB is the source voltage for the base, and the VCC is the source voltage which is connected to the collector terminal. And this voltage VB defines the difference between the voltage at the base and the emitter terminal. So this voltage VB can be defined as voltage VB minus VE. So if the voltage at the base terminal is, let's say, VB, and the voltage at the emitter terminal is VE, then the voltage VB can be defined as voltage VB minus VE. And here, this voltage VB and VE are measured with respect to the ground terminal. Similarly, this voltage VC can be defined as the collector voltage VC minus VE. So instead of VB, if you write voltage VEB, then it can be written as voltage VE minus VB, and this voltage will be negative of the VBE. So throughout our discussion on the BJT, we will use these notations. So here, this base voltage and the collector voltage is applied in such a way that the base emitter junction will get forward biased and the base collector junction will get reverse biased. That means over here, the BJT is biased in such a way that this voltage VB is positive and this voltage VCB is also positive. Now, if you notice over here, this is the PN junction. So whenever this PN junction is forward biased, then the typical forward voltage drop across this diode is in the range of 0.6 to 0.7 volt. That means whenever we forward bias this base emitter junction, then the typical voltage drop between this base and the emitter junction will be roughly around 0.7 volt. Now once we apply this biasing voltages, then the electrons from the emitter will be pushed towards the base terminal, because as I said earlier, the emitter is the heavily doped. That means the emitter has a large number of for them, but enter electrons, that means will enter into the collector region. Now if you notice over here, once the electrons from the emitter enters into the base region, then they will become the minority charge carriers. And if you see over here, the base collector junction is reverse biased. So due to the applied electric field at the collector terminal, these minority charge carriers or the electrons will get attracted towards the collector terminal. So once the electrons enters into this collector region, then they will get attracted by the positive terminal of this VCC. So if you see the direction of the flow of electron, then from the emitter, the electrons will flow in this direction, and most of the electrons which is emitted by the emitter will get collected by the collector region. And very small amount of electrons only will flow in. This will often be I. Then we can say that this base current IB plus alpha times IE is equal to IE. That means the base current IB is equal to 1 minus alpha times emitter current. And once again, if you put the value of I in terms of the collector current, then we can say that the base current IB is equal to 1 minus alpha times IC divided by alpha. That means the base current IB is equal to 1 minus alpha divided by alpha times collector current. Or we can say that the collector current IC is equal to alpha divided by 1 minus alpha times base current. And let's say this is equal to beta. That means the collector current IC is equal to beta times IB. So this beta is known as the current gain of the BJT. And typically, the value of beta varies from 50 to 400 for the different transistors. So from this we can say that IB plus IC, that is equal to emitter current. That means base current IB plus beta times IB is equal to I. That means the emitter current I can be given as beta plus 1 times IB. So this is the relationship between the base current, emitter current and the collector current. Now if you notice over here, in this common emitter configuration, this base current is the current on the input side, while the collector current is the current on the output side. And these two currents are related by this expression. That means by controlling this base current on the input side, it is possible to control the collector current. And that is why these bipolar junction transistors are known as the current control device. That means just by controlling the input current on the base side, it is possible to control the output current. On the other hand, if you see the other type of transistor, that is the field effect transistor, it is the voltage control device. That means in that case, by controlling the input voltage, it is possible to control the output current. Also, if you notice over here, in this configuration of the BJT, the output collector current gets amplified by the factor of beta. And if you connect the resistor between the collector and the emitter terminal, then it is possible to amplify the input signal. That means after biasing the BJT in this configuration, if you apply the AC signal at the input, then it is possible to amplify that signal. And we will discuss about it in detail in the upcoming videos. Now during our discussion, we haven't considered the current due to the minority charge carriers in this collector region. Because if you notice over here, this base collector junction is reverse bias. So for a moment, if we remove this emitter connection, then the current which is flowing through the collector is only due to the minority charge carriers. And let's say this current is equal to ICO. So this current is similar to the reverse saturation current which we have seen in the P-N junction diode. So the total collector current ICT will be equal to the IC plus ICO, where this ICO is the current due to the minority charge carriers. And typically, this current is in the range of microamperes, while this collector current IC is in the range of milliampere. So this is all about the different types of currents in the BJT. So in the upcoming videos, we will see the different configurations of the BJT as well as the input and output characteristic of the BJT. And we will also see how the BJT can be biased using the different techniques. But I hope in this video, you got the brief overview about the BJT. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video,
Hello friends, welcome to Engineering Funda family. In this video, I'm going to explain you Eber small model for BJT. And to understand Eber small model, I'll be considering P and P transistor. So you can observe we are having P and P transistor. This is emitter terminal, this is base terminal, and this is collector terminal. This is emitter base junction, that is JE, and this is base collector junction, that is JC. In terms of concentration, emitter is having highest concentration, and in terms of size, collector is having highest size. Now, to understand working of this transistor as per Eber small model, I'll be considering this PN junction, and based on this, let us draw equivalent circuit first. So here we are having emitter terminal, here we are having emitter terminal, and at emitter terminal, if you observe, we have PN junction. So let us draw one diode as PN junction, and this diode is named as emitter junction. So I'm saying that is DE. And after this, here if you observe, we are having NP junction, that is base collector junction. So here another diode that one can draw, that is like this, as it is base collector junction as per NP. So NP means that is how diode will be there, and this is collector terminal. And name of this PN junction that will be as per JC. So I'm saying this is DC. And in between this, we are having base terminal. So let us plot base terminal here, right? So this is base terminal. So that is how equivalent circuit that we can draw. But one thing that we need to understand here, see in this circuit, current passing through this diode has no relevance with current passing through this diode, and current passing over here at emitter is having no relevance of current passing through this base. But one thing that you need to understand here, see in this circuit, current passing through this diode has no relevance with current passing through this diode. And current passing over here at modification that you need to add along with the circuit. So that modification is there based on dependency. Now how dependency is there? Like you see, as if you talk about emitter current, then emitter current that is having dependency based on collector current. Even if you talk about collector current, then that is having dependency over emitter current. Practically this circuit is having no dependency. If you say here some current is passing, then that current is having no relevance on this diode. But in transistor that is happening. So how to add those dependency? Let me explain you that. See here, if you talk about current passing through this diode, let us say over here that is IF. And in this diode, let me consider direction like this. So this is IR. So how dependency is there? So as if you talk about active region, then in active region, when emitter current flows, at that time, current will be also flowing through collector and it will happen in this direction. So here what I'll do is, I'll be considering one current source, which explains you current will flow through collector, right? And the value over here, that will be as per current passing through this diode, current flowing over here at emitter. So it will be alpha F, it will be alpha F, IF. And if you talk about reverse active mode, so in reverse active mode, current will flow through collector. And see, here there will be relevance at current passing at emitter terminal based on collector current. So how to add that relevance? By adding current source. So let me add one current source here, right? And that current source that you can observe, it is having direction like this. And here that will be alpha R, IR. So current passing through this collector junction, that is having relevance over here, right? Now, see, this is what the model which I have. Current reverse active mode, current will flow through collector. And see, here there will be relevance at current passing at emitter terminal based on collector current. So how to add that? Current will be also flowing through collector and it will happen in this direction. Then in active region, when emitter current flows, at that time, current will be also flowing through collector and it will happen in this direction. So here what I'll do is, I'll be considering one current source, which explains you current will flow through collector, right? And the value over here, that will be as per current passing through this diode, current flowing over here at emitter. So it will be alpha F, IF. And if you talk about reverse active mode, so in reverse active mode, current will flow through collector. And see, here there will be relevance at current passing at emitter terminal based on collector current. So how to add that relevance? By adding current source. So let me add one current source here, right? And that current source that you can observe, it is having direction like this. And here that will be alpha R, IR. So current passing through this collector junction, that is having relevance over here, right? Now, see, this is what the model which I have discussed about forward active and reverse active. But practically, this is also applicable to all other regions. Like transistor can work in forward active, reverse active, as well as cutoff and saturation region, right? So for all four modes of operation, this circuit is applicable. Now, to understand this circuit in terms of equations, here let us consider this diode which is having applied voltage as per plus minus like this, and that voltage should be VBE, right? And over here with this diode, polarity will be minus plus like this, and here should be relation 2, and here that will be, so here that reverse active mode. So in reverse active mode, current will flow through. How to add that in direction like this, right? Now, see, this is what the model which I have discussed about forward active and reverse active, but practically this is also applicable to all other regions. Like transistor can work in forward active, reverse active, as well as cutoff and saturation region, right? So for all four modes of operation, this circuit is applicable. Applied voltage as per plus minus like this, and that voltage should be VB. Let us consider this diode which is having applied voltage as per plus minus like this, and that voltage should be VBE, right? And over here with this diode, polarity will be minus plus like this, and here voltage is VCB, right? And see, in terms of terminal, let us consider current direction. So here we are having current IE, here let us say we are having current IC, and here we are having current IB, right? So in terms of this transistor, you can say here current is IE, here current is IC, and here current is IB. See, that is how things are there. What I have done is I have drawn the equivalent circuit in form of diode over here from these three layers, right? Now, first of all, we need to understand how much emitter current is flowing over here. So for that, what you need to do is you need to understand how much current is entering here at this node and how much current that is leaving from this node, right? So let me have another color. Let us say this is a junction. This is having junction number 1, and let us say this is junction, that is junction number 2. So here what I'll do is I'll apply KCL at junction 1. Apply KCL at 1. So if you apply KCL at 1, entering that is IE, and entering current is alpha R IR. So alpha R IR, that is equals to leaving current is IF. So based on this, you can say IE current, that will be IF minus alpha R IR. I'll explain you this currents in detail even in this video itself. Let us apply KCL at node 2 even. So now I'm going to apply KCL at node 2. So entering current, that is alpha FIF, and leaving current is IC and IR. So IC plus IR, that is equals to alpha F IF. So from this you can say IC, that is alpha F IF minus IR. Right. Now here in this equation, we need to understand how to write this currents. Like what is IF? So IF is current passing through diode DE. Right. So you should know what is diode current equation. So diode current equation, that will be current passing over here due to minority carriers into e to the power voltage applied divided by Vt minus 1. Let me explain you how it is there. So if you talk about this P due to minority carriers, know what is diode current equation. So diode current equation, that will be current passing over here due to minority carriers into e to the power voltage applied divided by Vt minus. As per emitter, you will have to mention the current. Right. So here what I'll do is I'll be writing this IF as per UC. This IF, that will be as per current due to minority carriers over here. So that is IEO into e to the power voltage applied across this diode, that is VBE. So VBE divided, that is IEO into e to the as per UC. This IF, that will be as per current due to minority carriers over here. So that is IEO into e to the power voltage applied across this diode, that is VBE. So VBE divided by eta VT, right, and minus 1. See, that is what IF, right? And see, minus alpha R and IR is there. Now what is IR? IR is current passing through this diode like this. So through this diode, current is how much? Current is based on minority carriers due to collector, right? So that will be ICO. So let us write this current as ICO into e to the power, what is the voltage which is applied over here? VCB. So e to the power VCB divided by eta Vt minus 1, right? And this is what we need to apply over here as well. So let me note it down in this even. So this alpha F into IF. So IF is this minus IR, and IR is this ICO into e to the power VCB by eta Vt minus 1, right? So that is how we can have equations of current. Now these equations of current, IE and IC, these equations of current, you see. So these equations are also applicable to all other modes. Let me explain you how it is applicable. So when you want to understand this current, then you see, as if you talk about forward active. So in forward active, this IF will be IEO into this only, right? But in forward active, see this current passing through this diode. That will be happening in this direction, and that will be due to reverse recovery current. So in that situation, this current, that will be due to reverse recovery current. You can say ICO only, right? You don't need to have this. This is what you have it when current, that we calculate like this. But in reverse bias, this current, that will be ICO only, right? Here you see this VCB that is having this polarity. In active region, this diode will be there in forward bias, this diode will be there in reverse bias. So in forward bias, you have to mention current like this, but in reverse bias, current will be only IEO as if you talk about DE diode, and current will be ICO as if you talk about DC diode. That is how things are there. So now once you have idea like forward active means this junction forward, this junction reverse. If you talk about saturation, both are forward. So as if both are forward, these are the current equations that you need to consider for calculation, right? If you talk about cutoff, then in cutoff, both of these diodes are reverse. So as if both are reverse, then see in this current equation, instead of this, you just have to write IE only, and instead of ICO into this, you have to write ICO only, right? So that is how things are there. So these equations are applicable to all the conditions. That is what I mean to say over here, right? And if you talk about base current, then base current will be how much? Base current will be IE minus IC, right? So that even you can calculate from this equations. Still, if anything to share, please note it down in comment section. I'll be happy to help you. Thank you so much for watching this video.
In this video, we're going to see a small model of a BJT. So to start with, let me take the PNP BJT that we have been seeing all along the course. Now the question is, can we model this PNP transistor in a simple model so that it represents this BJT in terms of large signal model? If you observe here, we have an emitter junction in between emitter and base, which is a PN junction. So we can say this is a PN junction. So let me draw a PN junction here, saying this is similar to the PN junction that we have here near the emitter, which is emitter junction. And we have another PN junction, which is here that we call as collector junction between the collector and the base. So let me represent that also. That is a PN junction we have here. So we can say this is emitter terminal, this is collector terminal, and the one in the middle, the base terminal. Now let me call this diode as the emitter diode, just for our reference, and this is the collector diode. If we take two diodes and try to connect in this fashion, obviously they wouldn't be working as a BJT that we have on the left side, because this first diode DE cannot control what happens in DC, the collector diode. And the same thing happens here, that DC cannot control what happens in DE if you have two diodes connected in this fashion. Whereas in BJT, the two junctions are interacting junctions, because the current flowing in collector junction is controlled by the current flowing through the emitter junction in active mode. So hence we cannot simply say junctions are interacting junctions. Now we have some current that flows to collector junction called alpha F. Now our intention is not, so let's represent that as a, on this current, let's say which is IF. Now we have some current that flows to collector junction called alpha F times IF. So let's represent that as a current dependent current source here. That is alpha F times IF. Now our intention is not to just model BJT in active region of operation. So let's say we have inverse active region of operation, where the collector junction is forward biased and the emitter junction is reverse biased. In which case the current that, so let's say we have inverse active region of operation, where the collector junction is forward biased and the emitter junction is reverse biased. In which case the current that is flowing through the collector junction, let's call this as IR, because R represents the reverse active mode of operation current flow, and F here represents the forward active mode of operation current flow through the emitter junction. Now because there is IR flowing through this, there would be current flowing through the emitter junction which would depend on this IR. That we can represent with a current dependent current source. Let me represent that here. This is alpha R times IR. Now let's call the voltages across these diodes as VEB and across this diode as VCB. Now we have seen that this model would work for forward active and reverse active, and we would go forward and even find out that this model would be valid for even saturation and cutoff. But let me mark the currents here. This is the emitter current, this is the collector current, and this is the base current. Now the model that we have here is called Abers-Moll model. We started with two PN junction diodes which are not interacting, but in case of a BJT they would be interacting. To show that, we have shown here the current dependent current sources with alpha F and alpha R parameters in terms of IF and IR respectively for forward active and reverse active modes of operation. Now the diodes that we are showing here are assumed to be ideal diodes which have ideal diode current equations. Now having said that, let's write the equations for emitter current, collector current, and base current. Starting with emitter current, IE is equal to IF minus alpha R times IR, which can be written equal to, of course IF is the equation of the second diode, which is DC. So that is IC naught times e power VCB over VT minus 1. Now coming to collector current, IC is equal to alpha F IF minus IR. We can write this equal to alpha F times IF is IE naught times e power VEB over VT minus 1 minus IR is IC naught times e power VCB over VT minus 1. Now coming to IB is equal to IF plus IR minus alpha F IF minus alpha R IR. So if we segregate this, we get IF minus alpha R IR minus alpha F IF minus IR, which is equal to IE minus IC, all modes of operations. Now IE naught here is the leakage current through the emitter junction, and IC naught is the leakage current through the collector junction. Now to understand what these terms are equal to, in terms of, to find out what is IE and IC in active region of operation, because we have these terms are equal to in the leakage current through the emitter junction, and IC naught is the leakage current through the collector junction. Now to understand what these terms are equal to in terms of the device parameters, so let's correlate with them and find what these quantities are. JC is reverse biased, which means E naught times e power VEB over VT. We would have IC is equal to C naught, because the collector junction is reverse biased, hence we will have reverse saturation current there, negative over VT minus 1. Now we would get plus IC naught, because the collector junction is reverse biased, hence we will have reverse saturation current there, negative of negative positive, hence we got plus IC naught. Now let's get the similar equations. So let's get the similar equations from the previous video where we derived. The equations are, now looking at this, we can say that alpha R IC naught should be equal to H naught, because it means we can represent IE naught is equal to IS over alpha F and IC naught as IS over alpha R. Now having known these expressions, now let's rewrite the equations that we had. Those are the initial equations we had here, that is number 1 and number 2, which are valid in all regions of operation. In fact, to find out the relationship, we just took active mode of operation because we had the equations derived from previous video. Hence, we use them here to find the relationships. So let me rewrite those equations here. Now, if we observe these equations, we have IS as a parameter that we need to know to find these equations, and of course alpha F and alpha R. Apart from that, it's all about the applied potentials at emitter base junction and collector base junction, VEB and VCB respectively. So the number of parameters that are present in these equations are, in fact, very less. Now we can rewrite these expressions in terms of beta F and beta R, where